we have been talking about field of a point charge moving with velocity v, and we have derived the corresponding scalar and vector potentials. With those derived, we are now in a position to obtain the electric and magnetic fields of a moving point charge. So, this lecture is going to be on the electric and magnetic fields of a moving point charge. Earlier, we had calculated these fields for a point charge moving with uniform velocity. The difference between that and today's lecture is going to be that the velocity of the point charge is time dependent, and therefore, it may be accelerating, which will give rise to radiation, as we have already seen in the past, or moving with uniform velocity, which should be a part of this entire derivation. So, let me first recap, and to make our calculations easy, let me define certain terms so that bookkeeping is easier, and then obtain these fields. So, what we considered in an earlier lecture was there was a point charge q, which is moving with velocity v t, and we wanted to get a field at a point position r at time t. At that time, the point charge is where it is shown. However, because of the finite speed of propagation of electromagnetic waves, the field at this point is calculated by the position of this point charge at an earlier time. This I am going to call r naught at t retarded, so that this distance is r minus r naught t retarded. So, whatever I see at time t at this point is given out by the charge at a position which is slightly earlier than its current position, and the expressions for these fields were phi, the scalar potential R t, is equal to q over 4 pi epsilon 0 1 over modulus r minus r naught t retarded times 1 upon 1 minus n dot v over c, where n is this unit vector in the direction of r minus r naught at t retarded divided by the distance r minus r naught t retarded itself. So, the unit vector is in the direction shown here. Similarly, the vector potential A r t is given as mu 0 q over 4 pi v calculated at t retarded divided by this entire thing r minus r naught at t retarded times this factor 1 over 1 minus n dot v calculated at t retarded divided by c. To keep our notation simple, so that we do not have to write so many terms again and again, we are going to define the distance r as the distance from r to r naught. Everything is being calculated at t retarded, and I keep saying it because this is a very important point. And in fact, when we calculate the potentials, in fact, when we calculate the electric field or the magnetic field, we calculate the derivatives with respect to t retarded. R vector itself is r minus r naught t retarded. Then I am going to define a quantity beta which is usually used in the books, which is velocity vector divided by c, dimensionless. And beta dot is the time derivative of beta, which is going to be equal to v dot over c. And I am going to define a distance s, which is r times this factor 1 minus n dot v over c. Again, everything being calculated at retarded time. So, this is r 1 minus n dot beta, which is then equal to r minus r vector itself dot beta. So, we have defined all these quantities so that we can write the expressions for the potentials in a much shorter way. Let us do that now. So, what we are considering is this charge, point charge q, moving with velocity v t, and again pictorially I will show you what all the distances are. Here is vector r, where I want the potential at time t, and from the retarded position to this point is the vector capital R, and this position is r naught at t retarded. And then I can write my phi r t as q over 4 pi epsilon 0, and if you look back from the quantities that I defined, this is 1 over s. And similarly, the vector potential A r t is equal to mu 0 q over 4 pi v being calculated at t retarded over s. Again, s is being calculated at t retarded. Everything is at t retarded. Again, remind you that s is equal to r minus beta dot r, where beta is v over c. Once I have written these potentials, then the electric field E r t is going to be minus grad of phi r t minus d a dt. And similarly, the magnetic field B r t is going to be curl of A r t. Very simple thing to do, except there is a problem. And therefore, one has to be a little careful in taking these derivatives. The problem is the definition of retarded time itself. Retarded time T r is T minus modulus r minus r naught T r divided by c. So, you notice that T r depends on a quantity that itself depends on T r. So, it is like you can keep making a series which will be converging, but T r appears on both the sides. So, it is very difficult to calculate, the quantities related to derivatives of t, because you have to take care of T r. So, let me write the difficulties first. 1, when derivative grad, so with respect to r is taken, t is kept fixed. Number 2, quantities like position r naught t of the particle, velocity of the particle, acceleration of the particle are given in terms of T r. Number 3, T r depends on r. And therefore, when I take the derivative with respect to r, I have to vary T r. T r cannot remain fixed. T remains fixed, but T r does not remain fixed. And we are interested in calculating the derivatives with respect to T r. So, you see this whole thing is kind of entangled together, and we have to find a way of doing these derivatives properly. Let me explain it through a figure. So, here is the particle. Moving with velocity v t, and from the retarded position you have r, and I have this position of the place at r. When I vary r, let us say by delta r, let us say this is delta r, all the quantities change on two counts. One, because I have changed this position, so this is one change. And other thing is, for this point, T r is going to be different. T r is going to be different for the new point at r plus delta r. So, I am going to change the quantity on two counts. When I take this derivative, I am going to change, because r is changing, plus I am going to change by chain rule. I write it like this, because T r is changing. If grad of T r were 0, then grad would be equivalent to grad 1. Or if derivatives were taken with respect to r and t, then also grad would operate simply on something dependent on r. But I want derivative with respect to r, and the two are related, but we want variation with respect to T r, because again, as I said earlier, r naught T r, v naught T r, and a T r are in terms of T r. And therefore, when I take derivative, I want to see how acceleration or velocity change in the past time, and grad of T r is not equal to 0. And therefore, what I said here, these two things are related. So, that is the subtlety that is involved. Furthermore, if I change the time, because I have to take derivative with respect to time also, if I change t, second point, if we change t, this also implies T r changes. So, let me summarize all this that I said. 1, we wish to express everything in terms of r and T r. Number 2, grad T r is not 0. T r changes as r changes. And this has to be accounted for. And that is why we wrote that grad with respect to r is going to be grad 1 plus grad TR partial derivative with respect to TR. The TR changes, and you have to then include how TR changes with time. So, that is grad TR. What is grad 1? Grad 1 acts only on R or explicit functions of R and R alone. So, we are treating R and TR separately. So, there is an explicit dependence on R and there is a dependence on R through TR, but that dependence on R through TR is being taken care of by the second term in the derivative. So, again let me write, because this is a subtle point, grad equals grad 1 plus grad TR d by TR. This one, the first term is explicit dependence on R. The second term is also dependence on R, but through TR. So, dependence on R through TR. And we have to be careful in taking these derivatives. So, that is settled. Now, we are ready to do our calculations. So, first we will calculate the electric field. The electric field ERT is given as minus grad of phi minus dA dt. And as I said earlier, we would like to bring in R and TR. So, let us calculate these terms one by one. We will calculate first grad of phi, the minus sign, which is grad of q over 4 pi epsilon 0 1 over s, which I can write as q over 4 pi epsilon 0 1 over s square grad of s. So, everything else is accounted for. Now, we need to calculate grad of s. Grad of s, as we said earlier, is going to be grad 1 operating on s plus grad of TR ds dTR. So, we will calculate these quantities one by one. S we call as R minus R dot V over C, or R minus R dot beta. R vector is modulus R minus R naught TR. So, first let us calculate grad 1 of S. This is an explicit derivative with respect to R alone. So, this is grad with respect to R of R minus grad with respect to 1 of R dot beta. Beta depends only on TR, so del 1 does not operate on that. And this comes out to be R unit vector minus beta. I leave this for you to show. Quite a simple calculation, but you must do it. So, we found grad 1 S. Next, we want to find grad of TR. To find grad of TR, I am going to make use of the retarded time equation. So, TR is T minus R over C, and therefore, TR minus T is equal to minus R over C. When I apply grad operator on this, I am going to get grad of TR minus 0, because T and R vary independently, is equal to minus 1 over C grad of R. R and T are independent. So, let us work on this. So, I found grad of TR is equal to minus 1 over C grad of R, which again I can write as minus 1 over C grad 1 acting on R minus grad of TR dr dTR. Notice that grad of TR now has appeared on both sides, like summing a series. So, I can bring it to the other side and calculate what grad of TR is going to be. But for that, I first need grad 1 of R and dr dTR. Grad 1 of R is unit vector R, and dr dTR is d by dTR of R minus R naught TR, which is going to be equal to R unit vector dot V with a minus sign. Again, show that partial R partial TR is equal to minus R unit vector dot V, again calculated at TR. Putting all this in, we get grad of TR is equal to minus R unit vector over C, then I get minus minus plus grad of TR times R unit vector dot V over C, which gives me grad of TR 1 minus R unit vector dot beta is equal to minus R unit vector over C, and that leads to the expression for grad of TR, which is equal to minus R unit vector over C 1 minus R unit vector dot beta. If I multiply this by R over R, in the numerator and the denominator, this becomes minus R vector divided by C S. So, you found what grad of TR is. Grad of TR is equal to minus R over CS. Having done all this, I can now write therefore grad of phi RT with a minus sign in front equals Q over 4 pi epsilon 0 1 over S square grad 1 S plus grad TR del S by del TR as equal to Q over 4 pi epsilon 0 1 over S square. Grad 1 S I have already calculated to be R minus V over C plus grad of TR which I have calculated to be minus r vector over c s times del s del T r. So, one term is now remaining to be calculated. We will do that now. So, ds dtr is partial derivative with respect to T r of r minus r dot, let me explicitly write this, v over c. dr by dtr we have already calculated to be minus r unit vector dot v minus I have dr by dt dot v over c minus r dot v dot over c, where v dot is equal to dv dtr. So, ds dtr comes out to be minus r unit vector dot v minus v square over c minus r dot v dot over c. Let us see if there is a mistake. dr by dt, this is with a plus sign, because r naught comes with a minus sign. So, this is ds by dtr, and therefore, minus grad phi RT is equal to q over 4 pi epsilon 0 s square times r unit vector minus v over c, which I can write as beta, minus r vector over c s times minus r unit vector dot v plus v square over c minus r dot v derivative divided by c, which is equal to q over 4 pi epsilon 0 s square r unit vector minus beta plus r over s r unit vector dot beta minus r unit vector over s beta square minus r over c s, minus minus will become plus r vector dot v dot over c. So, I can make this c square and remove this. That is minus grad of phi. Next, we need to calculate the derivative of vector potential with respect to time. So, this is all being calculated at retarded time. Next, we need to calculate the derivative dA dt, that is the time derivative of the vector potential, which will be given as dtr dt times dA dtr. Keep in mind that again we are changing the derivative of the vector potential to derivative with respect to retarded time. Now, I will calculate both terms one by one. First, let me calculate dtr by dt. So, let us calculate dTr by dt. For this, I will again use the condition that Tr minus T is equal to minus R over C, and if I take the derivative with respect to time, on both the sides I get partial derivative dTr by dt minus 1 is equal to minus 1 over C dr by dt, which is equal to minus 1 over C dr by dTr by dt again. So, notice that this term dTr by dt is occurring on both the sides, and therefore, I can calculate it. What was dr? dTr? This we had already seen was equal to minus r unit vector dot v, and therefore, I get partial derivative dTr by dt minus 1 is equal to minus 1 over C, minus minus will become plus r unit vector dot v times dTr by dt, and this immediately gives me partial derivative dTr by dt equals 1 over 1 minus r unit vector dot beta. And again, if I multiply by r, this becomes equal to r by s. So, I have gotten the first term. How about the second term? The second term, partial derivative dA by dTr is equal to mu 0 q over 4 pi d by dTr of v dr over s, which I can write as mu 0 q over 4 pi v dot over s minus 1 over s square v ds by dTr. And we have already calculated ds by dTr. ds by dTr is equal to minus r unit vector dot v plus v square over c minus r dot v dot over c. So, we have all the terms now to obtain dA dt, and that gives me dA dt is equal to mu 0 q over 4 pi. Inside I have v dot over s minus v over s square times minus r unit vector dot v plus v square over c minus r dot v dot over c times r over s. So, we have gotten dA dt also, and therefore, the electric field E, which is minus grad phi minus dA dt, can be easily calculated, and I will leave that for you. So, I just want to point out at this point that I have been very careful in deriving all the results, but still there may be some sign mistakes or something. So, please check these. the final result that comes out from here, that E comes out to be a term which is dependent only on V and plus a term which depends on the acceleration and V both. So, let me write this. This is the term that is dependent only on V, and the term on the right hand side is depends on the acceleration and V both, and it is this term that gives rise to radiation. So, when you combine all this, you get E equals EV plus EA, where EV has a very simple form, comes out to be equal to Q over 4 pi epsilon 0 R minus R V over C divided by S cubed 1 minus V square over C square. In terms of parameter beta, it can be written as Q over 4 pi epsilon 0 R vector minus R beta divided by S cubed 1 minus beta square. That is the V dependent term. Since R has dimensions of L, S has dimensions of length again. So, EV is proportional to 1 over length square, like the static field. And this, you can check, has the same form as derived by Lorentz. For V much less than C, this expression goes to EV equals Q over 4 pi epsilon 0 R vector divided by S cubed 1 minus V square over C square. On the other hand, E acceleration comes out to be Q over 4 pi epsilon 0 R square over C square S cubed multiplied by R unit vector dot V dot R unit vector minus V by C minus S over R V dot. And this is proportional to 1 over length. This gives rise to radiation. So, you can see that the field related to radiation comes from V dot. If V dot is 0, there will be no radiation. This term is conveniently written as E A equals Q over 4 pi epsilon 0 R square over C square S cubed R unit vector crossed with R unit vector minus V by C cross V dot over C. So, this has all these cross products, and you can see this is perpendicular to R. For all this, what I have followed is the description given in book by T. L. Chow, Introduction to Electromagnetic Theory. All the notation, all the derivation, everything is taken from here. This I found to be intuitively very appealing. There are various ways of deriving the same expressions. Griffiths has one, Zangwill has one. Jackson talks about a different way of doing it, basically a relativistic approach where the fields are calculated in the charge frame and then transformed into the lab frame. But I found this to be a very transparent and intuitively appealing approach, and so I took this. Now, in the same manner, now I can calculate the B field, which is curl of A, and again keep in mind that this term curl, the operator is with respect to R alone plus grad T R, which we have calculated d by dt R, and therefore, the B field is going to be del 1 plus del T R d by dt R cross A, and when you calculate this, it is going to be equal to grad 1 cross A plus grad T R cross d A dt R. There will be these two terms. And various terms occurring in this we have already calculated. The only complication now comes because there is a cross product. Grad A, grad T R, we can calculate. This we have already calculated. Del 1 cross A you can calculate. So, that calculation I will leave for you. The final result for both velocity dependent and acceleration dependent field comes out to be n unit vector cross E over C. So, this also is B V dependent plus B acceleration dependent. Once we have these, you can calculate all the Poynting vector, all the other properties. Keep in mind that BV and EV are 1 over length square dependent. So, they will not be contributing to radiation. The only term that will contribute to radiation will be the acceleration dependent term, which is 1 over R dependent, and therefore, the power going out with this term remains the same irrespective of how far from the charge you are. So, that represents radiation. So, I hope I have given you how to go about this derivation. The best way to do is to do it yourself once. I will be giving some problems in the assignment that will make you comfortable with this. So, let me now conclude this lecture by stating that 1, we have derived E and B for a moving point charge with velocity Vt care has been taken to account for T retarded dependence on R. The fields are V and A dependent, and a dependent term gives radiation. With all this derived, you can now find the properties of the Poynting vector, the power coming out, and so on, which will form part of your assignment. Thank you.